wander around Cement Creek yesterday. Learned a few things and found a few things. If anyone lost a really nice shoe up by the Upper Golden King Mine. And I also found an 8-ounce can of beer by the local mine, which disappeared when I got to my hotel room. So if that's yours, let me know and I'll buy a bigger one. Anyway, I've been coming down here since about 1995 with Brian Kimball and others, and some of you might be familiar with some of the data sets we've collected, basically mapping water quality spatially, doing synoptic studies on Mineral Creek and Upper Animas and Cement Creek. And these data sets have provided a lot of information on water quality and water chemistry. And we realized pretty early on that you need, the system's so complex that you really need models to understand the data sets. And so we spent a lot of time just kind of being science geeks and learning about the data and learning about geochemical processes. But over time, people, management type of people have asked us, well, can you use these models to answer questions? For example, what happens if we remediate a site? What's going to happen to water quality downstream? So we've kind of moved into that area of actually predicting and forecasting what might happen when you make some of these changes. And I'm going to talk about that today, and I'm also going to talk about the fact that if you're going to take this bold move to try to estimate what might happen when you do remediation, how good are these predictions? So we designed an experiment to actually look at how good these predictions might be. A lot of what I'll talk about today involves this model called OTAC. I just want to mention a couple things. This was funded by the USGS Toxic Substance Hydrology Program. And the people shown there in blue were really instrumental in getting this going. They had the foresight 20 years ago to make it happen. All right, so there's 3 parts to my talk. First, I'll just give a brief overview of water quality and the basic reactions that we're concerned about, and then how we develop this model, how it's put together, what the parts are. And then I'll briefly go over some model applications. As I said, initially we were just interested in the processes from a science standpoint. Eventually we moved on to water quality prediction as a management issue. And then finally I'll conclude with this idea of seeing how good these models are. So the first part here is just looking at the basic water chemistry and the reactions that happen and how the model fits together. As far as water chemistry goes, we've gone over some of this already, but basically you have mineralized ore, which is exposed to water and oxygen, and that in turn generates sulfuric acid, which lowers the pH, and at low pH, metals are much more soluble in water. For water quality samples, we generally deal with 2 different types of data. One is a total recoverable sample. So we collect a sample from a stream, and it contains both solid material and dissolved material. The solids can be made up of precipitates of iron and aluminum, and then also different elements absorb onto those solids. So precipitates of iron will absorb things like arsenic, lead, zinc, and copper. And then we also have a dissolved sample, which comes from filtration of the sample. And the key thing is that as pH goes down, the dissolved concentration of metals generally goes up. The other thing about dissolved metals is most of the water quality standards are in terms of the dissolved concentration. All right, so if you take a migrated sample and gradually raise the pH, so let's say you have a pH 3 water, many of you have seen the iron stains on the bottom of the stream, and that's from iron precipitation, which happens. And then as you come up higher in pH, you eventually precipitate aluminum, and then once you get into waters that things actually live in, you can absorb copper onto the iron or zinc onto the iron. So this generally is from pH 3.5 to 6.5. As you work your way up, you drop out these different metals. And the same thing happens in these watersheds. You might have the mother lode up here at the top of the watershed where you have some real acidic water. And then you have a clean tributary coming in which raises the pH some, and you get the aluminum precipitate. You get more clean water coming in farther downstream, and eventually you're absorbing things onto the solids in the water column. Here's an example of that from the Snake River by Keystone, Colorado. The Snake River in this first photo is on the left. It's an acidic stream. On the right is Deer Creek, a Coors beer, kind of clean water coming in. These two meet at a culvert, and the water from the Snake River has this orange precipitate on the bottom. The higher pH water comes in, the two mix, and in this zone here you start to get some aluminum precipitation. If you walk to the other side of the culvert, everything's mixed together, the pH is higher, and you get all this precipitate on the stream bed. So, as shown from this slide, we have a lot going on here. We have water moving downstream, and then we also have these reactions happening. So, we want to use a model to describe all the hydrology and chemistry going on, and that model is known as OTEC, which stands for one-dimensional transport with equilibrium chemistry. When I developed OTEC, at that time, if you wanted to look at things in streams, there were basically two types of models. There were these solute transport models, which were really good at simulating the hydrology, how things move downstream, but they weren't very good at the chemistry part. And then you also had chemical equilibrium models, which were basically what happens in a beaker, what's the pH, what happens when pH raises, do things precipitate and absorb. But the equilibrium models didn't do the transport part. So the logical thing was to combine the two. So OTEC combines the transport capabilities of Otis, which moves things downstream from segment to segment, with Mintec. So in each one of these segments, you basically have a beaker, and you can predict what the pH is, how much absorbs, how much precipitates, etc. Within OTEC, you're modeling pH, you're modeling aluminum, sulfate, copper, etc. And each one of those different components can be broken into a dissolved phase, a precipitated phase, and absorbed phase. And basically the model is a bookkeeping procedure where you keep track of these 5 phases and you move things downstream due to the flow, but you also can settle things to the bed. A key part of the model is this absorption algorithm, which considers the effect of pH on absorption. So basically as pH goes up, you have more absorption going on. And within OTEC itself, it's simulating the precipitation of iron and then the absorption of zinc, copper, arsenic, and lead onto that iron. All right, so that's the basic background on the model. As I said early on, we started looking at the science aspects. A lot of work done by in Leadville and the Snake River. But we've gone on to look at predicting post-remediation water quality. So we've done this in several cases. One was on Mineral Creek right here in Silverton, and these were just hypothetical examples we looked at. But then we also got real money to do these kind of predictions at Summitville, and then also Little Cottonwood Creek in Utah. And we have some plans to do similar activities on Cement Creek. So the key thing here is that whether you're doing the kind of science approach or the management approach is you really need to have good data sets to back these up. So most of you can't see this, but down at the bottom it says modeling without data is like blank without blank. And that's your homework to fill that in, I guess. So as I said, we start collecting these data sets that have a lot of spatial detail on the flow and chemistry, maybe say every 200 meters along the stream for 5 kilometers upstream or whatever. And we have this all through Mineral Creek and Cement Creek, etc. So these synoptic sampling activities we've done have these basically maps of hydrology and chemistry of the whole watershed. And so we can take all this information and feed it into the modeling procedure. And basically the modeling procedure is in 2 steps. The first is to take the existing data and recreate, do a simulation which recreates that existing data set. And this is called calibration. So, for example, you might have a couple of different inflows coming in this different reach. And you try different ones to see which ones make the model represent the data the best. And so that's how you calibrate the model. And then once you have the calibrated model, you can go ahead and play what-if scenarios. What if we plug this mine at it? What if we do active treatment? And what's going to happen downstream? All right, so a quick example. This is from Mineral Creek in '99. This is Phil Plank and myself, and it doesn't seem like that long ago, but we didn't have GPS at that time, so we walked the whole thing with a tape measure, and it's a lot of fun, actually. So this is from '99, and we're going to show you some slides about how we modeled this data set. So the objectives here is first quantify the hydrology, and so we use tracers in streams to get the stream flow at each point, so we have that data. And then we want to quantify the chemistry, and we use the data from our synoptic sampling to develop this calibrated model of existing conditions, how the stream functions right now. And then once we have that calibrated model, we can take the next step and evaluate remedial options. In the case of our 99 study, we had 38 stream sites. This is starting up by the Longfellow Kohler by Red Mountain Pass. We had a bunch of stream sites. We have chemistry and hydrology data on all this. One of the key inflows is actually water from the Longfellow Kohler at that time, came in at 209 meters. All right, so to model the existing conditions, first we have a whole set of chemical components, aluminum, arsenic, cadmium, etc. And then we specify reactions that are going to happen. We're going to model the precipitation of iron and precipitation of aluminum. And then we're going to model the absorption of these other metals like zinc and copper onto that iron and aluminum. And then the inputs to the model are the stream flow, which we have from our tracer, and the inflow chemistry. So different tributaries coming into Cement Creek, for example, or Mineral Creek in this case, represent what's coming into the system, and that's considered. And then finally, there's a database of equilibrium constants which describe the reactions. That's been developed over the years, and that's already part of the model. All right, so we fit the model to the existing data. The data is shown as points here. The x-axis is in terms of distance. And so, for example, the Longfellow Kohler water comes in and we drop the pH way down. And then as you work your way downstream, the pH gradually recovers. Same thing with metals. Longfellow Kohler water comes in, metal concentrations jump way up, and they're diluted. So once we have that calibrated model, we can go ahead and do the prediction. In this hypothetical case here, we said, well, what if we treat this water at the very top with a little treatment system, and instead of having this pH 3 water come in at the top, we're having pH 7 water come in. So basically, you take the calibrated model, put this new information in, which describes the remediation, and predict what might happen. So in this case, we looked at a couple different scenarios. They both resulted in really large reductions in metal concentrations, about 3.5 kilometers downstream. So anyway, that's a brief example. And I'm not sure where this quote comes from, but it's a keeper. And what I wanted to do is, it's pretty easy to sit in your office and learn about chemistry and write papers and that kind of stuff. But if you're going to take the step to actually predict what's going to happen after somebody spends millions of dollars for cleanup, it's a little more serious endeavor. So we designed this experiment to actually evaluate how good can we predict water quality. So basically, what happens when you calibrate the model is you're calibrating the model to this data that's collected under low pH conditions, and then your remedial actions often result in this really big increase in pH. And that's a whole other set of reactions kick in when you get up to those higher pHs. So that results in some uncertainty in the model. So how did we test the model? This was our basic approach in 2005, and we did a synoptic study just like we had done previously. So this is a paired synoptic study. The first study was just to look at existing conditions in Upper Mineral Creek. And so then we did that, and then the next day we started injecting sodium hydroxide into the stream. We had a couple 700-pound barrels of sodium hydroxide, which we had to dilute, and we injected it into the stream. And after doing that for about 24 hours, we did a second synoptic study where we sampled everything at the higher pH. So here's a diagram of the basic approach. We have our data from the first synoptic study under existing conditions. We use that to calibrate the model. Then we added sodium hydroxide, and I used the calibrated model to estimate what this post-remediation water quality might look like. Well, I had a bunch of coworkers here known as the Blind Trust, And they knew what this second data set looked like. The second data set is what happened after we added the sodium hydroxide. Anyway, they kept that data and didn't show it to me, and I predicted what would happen after remediation. And then once I had done that, I said, well, unlock the vault, release the data, and let's see how well we did. So lots of cool stuff happens when you add sodium hydroxide to low pH water. Here's the water running down, looks like antifreeze running downstream. Here's a little butterscotch pudding, all the precipitation happening here. Here's a site, it's a little hard to see with the light in here, but here's a site before and after. Here's the before shot, and here's the after shot. So at high pH, down in this pool, you basically have all these solids in the water column. All right, so to do the predictions, this is basically what I did. First thing I did is I wrote a long email to my coworkers. I said, well, this is exactly how I'm going to do things. And try to keep you to this because I don't want to cheat on this. This is an experiment to see how well we do. So I said, well, I'm going to get the pH from you at the top. Whatever the pH was after we added sodium hydroxide, give that to me, and I'll use that to model everything else. So they gave me the pH and alkalinity at the top, pH and all the metal data at the top, or pH and all the metal data lower down, I didn't know. And then I said I'm going to do a primary prediction, my best estimate. And I'm not going to, I know when the pH goes way up, this whole other set of reactions kick in, but I'm not even going to consider those. I don't want to be over-optimistic. I don't want to tell you this remediation is going to do a really good job and then have it come up short. So I'm just going to consider iron and aluminum precipitation as before. I'm not going to add a bunch of reactions. And then I'm going to let the model absorb things onto the ions. And then I said my measure of success is going to be the percent air. And I'm going to look at it at 3 different points along Mineral Creek. And then I was pretty sure I wasn't going to do a very good job just because of the complexities involved. So I said, well, I'm going to actually do, in addition to my best estimate simulation, I'm going to do 7 other simulations where I vary some of the parameters to see if I can develop a range of simulations, a range of predictions. All right, so here's some of the results. pH is shown on the left there, and my best estimate one is shown in red here, and as you can see, it does a pretty good job of simulating the post-remediation CD pH, excuse me. In terms of lead, again, pretty good job. The totals are shown in black here, and the dissolved is shown in red. So again, pretty good job. Here's a look at arsenic. Here's the calibration. Here's the primary prediction. So I'm way off on the totals, but I don't really care about that because that's the water quality standards are in terms of dissolve. And then you look at dissolve and you say, wow, look at this, I'm just nailing it. The line's going straight through the points. It's good. Well, it turns out if you zoom in on this data, all 8 of my simulations were actually below the data. And this was a 93% error according to the criteria I established before I did this. Not so good. Well, one thing I realized after having done this is that, well, yeah, this is a 93% error, but these are really low concentrations. And this is all below the water quality standards. So, is that really a bad thing? So I moved the goalposts a little bit closer, and I came up with a couple of different ways of looking at this. One is to look at the percent reduction, and one is to look at the water quality standards. And we'll go into that right now. So again, looking at arsenic, if I tell you that I'm going to reduce the arsenic concentrations by 99%, and in actuality they're reduced by 100%, there's some rounding here. If I'm off by a couple percent, you don't care. It's a huge reduction, and I'm in the ballpark basically. So I look at things that way, and you do a pretty good job. The other thing to do is look at the water quality standards, and there's basically 4 different possibilities. One is that I tell you I'm going to meet the standard for zinc, for example, and the observed data shows the exact same thing. So that's good, you correctly said. And the opposite is true. You can say we're not going to meet the standards and the data shows the same thing. That's good as well. But the worst case scenario is if I tell you we're going to meet the standard and we don't. So that's this type 1 error here. Well, it turns out, so listed here is aluminum, cadmium, copper, iron, pH, manganese, lead, and zinc. And out of these 25 different cases, we have 3 different sites that I'm evaluating. Out of the 25 different cases, as far as meeting the water quality standards, 19 of them were correct. In a couple cases, we had these severe type 1 errors. That was for manganese, and that's something I really wasn't paying much attention to anyway. And the other errors are these less severe errors where I say we're not going to meet the standard, and we actually do. So in summary, basically the estimates of post-remediation water quality for Mineral Creek were in the ballpark. 19 to 25 times we correctly predicted whether the standards would be met or not. And the real advantage of this approach is that you're modeling pH and iron and absorption on iron all at the same time. It's a complex system, and you're considering all those complexities when you do it. And that's it. I don't know if anyone can see this from the back, but at the bottom it says, it's the largest outhouse in San Juan. It's an 8-holer. And that's something Bill Sean told me in August 2005.